let's start today's session. Today's session is about associative operation. And we will see 2-3 algorithms on how to compute a linear algorithm in logarithm time. Okay. And we will also see how to compute nth Fibonacci number in log n time as well. Okay. So chapter 3 of the book is about associative operations. So as we discussed in final minutes of the last lesson, we have discussed what is associative operation. To revise, let's say star is a binary operation which takes two elements, let's say type T and type T for now, although it can take two different types, but for now, let's assume that operation takes two elements of same type and it returns type T. Okay. And obviously, we assume it is regular and all the usual stuff. You can refer to the book for more details. So, if an operation is associative, we can say that the order of operations doesn't matter in which we perform the operations. Like this is same as this is. So if an operation is associative, we can simply omit to place the braces or brackets. And the meaning is clear that what in whatever order we perform operation or star operation, the result will always be same. And we also covered the basic examples. Basic example for associative operation is addition, multiplication, matrix multiplication, matrix addition, and so on and so forth. And examples of known basic examples were like known associative operations were subtraction, division, and let's say vector dot product, vector cross product, and so on and so forth. So we have to deal with both type of operations, associative and non-associative operations. It is not necessary that every operation is associative or every operation is non-associative. Okay. But for our day-to-day life, for majority of the cases, we shall be dealing with associative operations, and due to its some good properties, we will cover what algorithms or structures we can get from associative operations. Okay. So next, one non-trivial example for someone who has not seen this, we are talking about. And if you are not aware what is a function composition, let's say f is a function. Let me write it this way. F is a function from type t, let's say x to y, and g is a function from type y to z. Then f or g composition f is simply this statement, and g composition f is a element from x to z. For instance, let's say I have two functions. One is function f, which uh, let's say makes the square, computes the square. Okay, for let's say floating point to floating point, and function g it simply add one to the input and returns, and it is also a function from floating point to floating point. So we have two type of composition. We can either have f of g or g of f. And let's me write the implementation wise, this will be equal to fx equal to x square, and implementation wise this will be equal to gx equal to x plus. Now what will be simply f of g of x. So basically if I have an input x to the function, let's say h1 equal to f of g, let me rewrite it. I have two functions, let's say h1 equal to f composition with g, and I have second function g composition with f. Now if I take x as input to h1, it means I am applying x to f of g, and by notation it is equal to f of g of x. Like first I apply g and then I apply f. Then what is it? G of x? G of x is x plus 1, and I apply f, so this will be equal to x plus 1 whole square. Coming to h2 of x, h2 of x will be g of f of x. So g f x. Now it is x square, so it is x square plus 1. As we can see, this composition operation is not commutative. And you remember what is commutative operation, and operation is commutative if we can change the order of operation. Like it doesn't matter in which order I apply the operation. Like I can rearrange the elements in any way, and the result will be same. So composition is not an commutative operation, but it is trivial to prove that composition is an associative operation. By associativity, I mean that f o g of h equal to f of g of h. It is a trivial exercise. I am not going to cover it. But the main intent of this exercise is to show you that we can combine various functions and they will also form associative operation. Like in programming, if we have written function g and function f, we can combine them as well and think of their composition or calling one function after another as some type of associativity if it benefits us. Okay. Now coming to the bonus structure, like I think author should have covered it. Maybe this topic is covered later in the book, but I thought that I should cover it now. Let's say I have A star B star C. In abstract syntax tree form, this is equivalent to this structure, right? And if I have this operation in abstract syntax tree, this is equivalent to this structure, right? And if ordering of applying operations does not matter, it means these two binary trees will give us same result irrespective of whichever whatever tree we choose. Okay, so let's say I have a very long sequence of operations. Let's say I am doing a1 star, a2 star, a3 star, a4 star, and so on and so forth. We will cover the case, and in next bonus session we will cover prefix sum algorithm and how to optimize the prefix sum. In, let's say, if we have unlimited resources or an unlimited amount of CPUs, we can compute prefix sum of an entire array in logarithm of n time. So my intent is to let you know that yes, we can, if we apply the theory to its extreme, we can make very unintuitive optimizations, like the optimizations which are not very clear from beginning, but once you see the pattern, it will make sense. Okay, so let's say the operation is left associative. I introduced two terms, one is left associative and one is right associative, and this is also covered in the next section of the book. So what is left associative operation? uh, it means that we are computing this value a3 star a4 star a5 and so on and so forth, or equivalently this is equivalent to a of n minus 1 operation, a of n minus 2 operation, a of n minus 3 operation, and so on and so forth, where the tree is left leaning, and in the end we have a0 and a1. Okay, and similarly now you can assume or guess what is right associativity operation. Right associativity operation is a1 star a2 and so on and so forth, where in the end terms are combined. Okay, and this will be equivalent to this tree, where by star I have a1 here, then a2 here, then a3 here, and so on and so forth. This tree is right leading. Now we have seen examples of non-associative operations, right? Where let's say minus and division were two prime examples of non-associative operations. So if I have to compute a1 minus a2 minus a3 minus a4 and so on forth, or a1 divided by a2 divided by a3 divided by a4 up to so on and so forth, or any other operation like which is not simple enough, it is possible that since it is not associative, that the result of applying operations like this is not same as applying operations like this. Okay, so in further section we will cover the algorithm to compute exactly these, like two separate algorithms, one to compute the value for the left associative application and one for right associative application. Next, for the optimization step, which I was talking about for the prefix sum, to give you an idea, so we have covered this thing that if an operation is associative, then we can form a tree. Like instead of being it associative, let me restate it. If the operation is binary operation, it is equivalent to binary tree. And if the operation is also associative, then it doesn't matter which binary tree we select, right? Because any operation or any sequence of operations will always give us the same results. Now imagine we have 2 raised to power k elements, or let's say 1024 elements, or around 1000 elements. So my idea is to compute, let's say, prefix sum of these elements in logarithm of n time. What I can do, I can arrange these elements on a line and create a complete binary tree where these are the array elements and these are pseudo elements, like the elements additionally present in the array, but you get the idea. We will cover it in further detail. So imagine that we have one CPU at each layer. Let's say these are the elements, and we have the CPU. This is CPU1, CPU2, CPU3, and so on and so forth. Similarly, on above layer, we have more CPUs, and on the top, we have one CPU. That's what I was referring to if we have unlimited resources or unlimited amount of CPUs. Although this is not purely theoretical, in case of GPUs, we have thousands of CPUs with us to perform this calculation. So we are still in the practical domain. Now imagine that in one step, all of these CPUs compute the associative, like all their values by combining these two values with star operation or the any associative operation which we are referring to. Then in next step, all the CPUs of this layer compute their values in next step, and so on and so forth till the root CPU compute its value. So how many steps do we take? We take a logarithm of n steps. And effectively, let's say our target was to compute the prefix sum of all the elements, or basically total sum of all the elements. Then by this algorithm, we can compute the sum of all the elements in logarithm of n time, right? And before next session, you can think of how we can extend same structure to compute the prefix sum. Basically, if I have elements, let's say A0, A1, A2, or A3, let's say I take 4 elements. How to compute A0? A0 plus A1, A0 plus A1 plus A2, and A0 plus A1 plus A2 plus A3. I have this array as input. I want to generate this array in logarithm of time. You can think about how we can do this. Okay. Now let's go to next session of the book, which is computing powers. So we have covered what is left associative and what is right associative, right? And let's say our operation is not associative and we want to apply the operation in left manner first, like from left to right. So how should we do it? So let's say we have these elements A0 star A1 star A2 and so on and so forth, and we are applying it like this. So if, and instead of distinct elements, for simplicity, we are assuming we want to compute A star A. Okay. You can extend the result for distinct elements as well. And we want to compute this value. So what we can do, if our n is 1 and precondition is n is at least 0, like at least 1. Okay. So if n is equal to 1, we don't have to apply any operation. We can simply return A. And by n, what I mean by this? In our notation, A star A is equivalent to A square. And A star A is equivalent to A cube. And A is simply A to the power 1. So the n is not how many times we are applying the operation, n is the power here. So if we are raising A with the power 1, then obviously the result will be A. Otherwise, what we can do, we can, let's think about very extreme term, and we have to, let's say, compute A to the power n. What we will do, A star A, then star A, then star A, and so on and so forth. Let's say our final term is like this. This is our entire expansion. If we have n terms in this sequence, we can say that A to the power n is equal to A to the power n minus 1 star A, right? And this is what algorithm is doing. It is doing what? We are recursively computing a to the power n minus 1 under same operation and apply operation with a. It is same as this notation, right? And similarly, you can compute the right associativity part. Okay. Next, coming to Mandry exponentiation. So we studied the structure of a tree, right? Now, I earlier stated that we in prefix sum we are going to work with distinct element, but let's assume we have all the elements that are same. Can we compute the multiplication of all the elements in logarithm time? And the answer is yes. For instance, let's say we have 16 elements, right? So 16 elements will form the base of this array, all the array elements. And then I have binary tree structure with 8 nodes on top. How many nodes are there? 8. Then 4 nodes on top, then 2 nodes on the top, and 1 node on the top. Okay. So what is this value represent? This represents a square. This represents a square. A square, a square, a square, a square, a square, and a square. This node represents a to the power 4, a to the power 4, a to the power 4, a to the power 4. This node represents a to the power 8, a to the power 8, and a to the power 16. This is when we compute the powers, like we compute, apply the operation on same element again and again, we can see that there is redundancy in entire cycle. And how to eliminate the redundancy? Let's say we want to compute a to the power 16. What we can do? We know that left element and right element are the same. So instead of computing left tree and right tree separately, what we can do? We can simply compute, let's say, right tree and take it square to compute the root value. This is the basic idea. So under this basic idea, we will be able to reduce computation of a to the power n in logarithm of n time. Very simple. Okay. So we have various cases and we are obviously assuming that n is greater than equal to 1. So if n is equal to 1, we know that a to the raised to power 1 is equal to a. Nothing much here. This is the base case. Now, if n is even, we can say that a to the power n is equal to a to the power n by 2 whole square. And this n by 2 is an integer, so we can compute it. So we can apply recursive function here. Again, if n is odd, then we can say, let's say n equal to 2k plus 1. So a to the power 2k plus 1 can be written by a times a to the power 2k, which is equal to a times a to the power k whole square. And we can compute a to the power k in log of k time or by recursive approach, right? So this is the basic idea. Next, we come to the algorithm. Now, instead of going into like if you are unable to understand or getting confused in these terms, let me write a simple algorithm and then you can try to fill in, okay, which part corresponds to which thing. Okay. So let's say we have power function which takes a and which takes n, and we are assuming for simplicity that star operation refers to anything that we are currently referring to. Okay. So I am saying if n equal to 1, then I will simply return a. This statement corresponds to this line. Okay. Now, if n% 2 equal to 0, this is this line. What does this mean? That n is even. So we can compute n by 2 first and then simply take the square of it. What we can do? We can return, let's say, let me make it bigger and change the pen color. This is the algorithm. If n is, what is this doing? Okay, n is even, then we can approach this thing in two types. Like either I can write it like this or I can write it like this, a square raised to power n by 2, right? So what I can simply do, if n is even, I will simply do a equal to a star a and I will return power of a comma n by 2. That's what this line is saying here, that we first compute a square, then we compute its power with n by 2. Now you get the idea. If we have, let's say, n is odd and n is, let's say, of the form 2k plus 1, then we can write a raised to power n equal to a raised to power 2k plus 1, which is same as a multiplied by a to the power square to the power k. So this is a square, this is a square whole raised to power n by 2, and this is a times a square raised to power n by 2, which is equal to a to the power n. with floor, right? So we can move forward. I believe you don't have any questions here. And again, from the complexity perspective, I have proved that this structure is similar to binary tree and perfect, like complete binary tree. And in complete binary tree, the complexity of this algorithm will be equivalent to how many different tree, like how many levels of tree are there. And since there are only logarithmic number of levels, we can compute the nth power in logarithmic number of times. And one application is given in the book. Why do we even care about computing this powers? So in RSA algorithm, this approach, like this algorithm is used at its core. Basically, we have to compute very large powers of given element under some modulus prime number. So this binary exponentiation drastically improves the performance of RSA algorithm, which is used in our internet cryptography and everything. Okay. So now let's go to next session. And this is simply program transformations. And this section cover various terminologies which are used to convert this recursive. So you can see that this function is calling itself again and again. This is a recursive function. By the sequence of transformations, the author has proved that the resulting iterative, basically without any recursion, we can write everything to compute nth power in a for loop or while loop. So this section refers to the techniques which are used to convert above recursive implementation into iterative implementation. And since there is nothing new from my side to add, you can refer the book or refer the internet on what these terminologies mean. Okay. Similarly, the book referred special case procedures. The intent of the author was that since we are assuming that, like, we have abstracted out the notion of integer. In this section, the author has given us some operations on integers that should be supported to use them in our algorithms. Nothing much else here. From theoretical perspective, yes, it matters. But if you are reading the book from practical perspective, then it is like you can read it once and get to know, okay, these are the properties that we are going to assume that any integer type will have. Okay. Next comes the concept of identity. So let me define an operation first. Let's say star is an operation of minimum of two elements. So if I say star A star B, it is equivalent to saying I am taking minimum of A comma B. Okay. And let's say this is star 1. And similarly, let me say star 2 is simply addition. So if I say A star 2 of B, it is equal to A plus B, where A and B are integers. Or any types where addition is supported. But let's stick to integers for now. Okay. So what is the identity element? Identity element means that, let's say E is the identity. And this has to be unique. Okay. So it means that A star E equal to A for all A. Alternatively, let's say I am talking about star 1, which is the minimum operation. So what should I place in this second place such that minimum of A comma that thing is same as A? For minimum, the answer is plus infinity. For addition, the answer is 0. Let's say it was simple multiplication, the answer would be 1. If it was matrix multiplication, the answer would be identity matrix. Let's say we are talking about 2 cross 2 matrices. Okay. So by identity element, we mean an element. If we apply that element in the operation, the result will be as if we have not applied the operation at all. That is the meaning of identity, and their use case is given in the book. Where, so earlier we saw that we specified a raised to power n for n, at least n has to be at least 1. Now we can extend this definition to include a raised to power 0 to e. Okay, so we can reduce the value of n in our algorithm. For instance, if I had to compute minimum, although for minimum it doesn't make sense to take minimum of same element again and again, but let's say I was talking about applying operation plus n times, what I will get? I will get n times a. Similarly, if I apply operation multiplication n times, what I will get? I will get a raised to power n. where a was the input element, right? So if I have to apply the operation zero number of times, I will simply return the identity of the operation. So for identity of a plus, we have zero. Let's see. If I apply the operation plus zero times, what should I get? I should get zero. And this also says that zero times a equal to zero. So it trivially translates. Similarly, let's say our operation was multiplication, and for multiplication, the identity is one. So if I apply operation zero times, n times n is zero, what should be the output? We know that a raised to power zero should be equal to one. Okay. And does our algorithm support that? Yes, definitely. If I also have the case of n equal to zero, identity element will be returned, which will be one in the case. Okay. So to cover base cases or corner cases, we have introduced identity, which simplifies our algorithm a lot. There are various use cases, but yes, again, there are parameterization of algorithms. You can refer the book. And let's come to main core algorithm of this book, which is computation of Fibonacci number, nth Fibonacci number in logarithm time. Okay. So we know that nth Fibonacci number is given by n minus 1th value plus n minus 2th value, where let's say we are taking this base. Okay. So if f0 equal to 1, f1 equal to 1, f2 equal to 2, f3 equal to 3, f4 equal to 5, f5 equal to 8, f6 equal to 13, and so on and so forth. And this sequence grow exponentially with some golden ratio as a basis, but let's not go into that. We want to compute nth Fibonacci number in log n time. How can we compute that? So let's say I write in matrix form. So what is fn? Fn equal to 1 times fn minus 1 plus 1 times fn minus 2, right? And fn minus 1 equal to 1 times fn minus 1 plus 0 times fn minus 2, right? Once you are convinced that this matrix is correct, we can move further. Okay. So if I rewrite this as f of n equal to f of n minus 1, and I write this matrix as A, what will I get? This is equal to A times fn minus 1, fn minus 2, which is same as A square of fn minus 2, fn minus 3, and so on and so forth, right? So equivalently, we can write fn of fn minus 1 equal to A raised to power n minus 1, f of 1, f of 0. This is my relation between nth Fibonacci number and first Fibonacci number in terms of matrix. So let me write it above. We can see that if our A matrix is 1, 1, 1, 0, then our fn and fn minus 1 vector is same as A raised to power n minus 1, and fn minus 1, f of 1, let me rewrite it, and f of 0. Now, since matrix multiplication is associative operation, we are computing nth power of same value. We can compute this value in logarithm time, where we know that multiplying two cross 2 matrices take O1 time, right? Fixed number of operations. So what we have achieved, we can write, and also f0 and f1 are denoted by 1 comma 1 are in the base case. So we can compute this in logarithm of n time. I will get a 2 cross 2 matrix. Then I will multiply that 2 cross 2 matrix with 1 1. Then I will get two values. First value will be our result, nth Fibonacci number. That's it. Nothing much more to do here. And linear recurrence, let me come to what are linear recurrences. Linear recurrences are equations of the form where fn depends on fn minus 1, fn minus 2, and up to fn minus k, where basically current term depends on some combination of basically a1, a2, ak, some linear combination of previous terms with base cases, appropriate number of base cases. If they are satisfied, then we say that it is a linear recurrence relation. And we have covered the algorithm to compute nth value of any linear recurrence in logarithm of n time. Okay. Now there is accumulation procedure, very short topic. You can refer the book. And in conclusion, we have algorithms are abstract when they can be used with different models satisfying the same requirements, such as associativity. We have seen various examples of this. We have seen simple a raised to power computing a raised to power n. We have seen computing n into a for if our operation is addition. if our operation is multiplication. And we have also seen matrix computation, like if we have to compute nth Fibonacci number, it is equivalent to computing nth power of some matrix, some 2 cross 2 matrix. Code optimization depends on equational reasoning. Unless types are known to be regular, few optimizations can be performed. If you read the book, like the sections which I have skipped, the meaning will be clear. Similarly, special case process can make code more efficient and even more abstract. So the combination, in summary, the combination of mathematics and abstract algorithms lead to surprising algorithms such that computation of log Fibonacci number in log n time, such as logarithmic time generation of nth element of linear recurrence. Right? And in next bonus session, we will cover computing prefix sum array in log n time. Can you even imagine that? Where let's say we have n elements, the ith element depends on all the values from 0 to I-1. So we have to basically, let's say we are talking about sum, we have to basically take sum of all the elements. How can we even take sum of n element or I elements in log of I time? It does not seem possible, but you will see that this is not a restriction. We can compress it further to logarithm of n time. Okay, see you in the next session.